Hi everyone. Let's say we have a non-conducting sphere that has a non-uniform charge density, rho, which is equal to b over r squared, where r is the radial distance from the center. And the value of this rho is within that non-conducting sphere. So I need to find and plot the electric field inside and outside that sphere, in addition to the voltage or potential inside and outside that sphere. So first, let's find the Q enclosed in a certain Gaussian surface. Let's say, for instance, I want to find the electric field at some point here. Since rho is positive, means the charge is positive inside, so the electric field will be away. And I need to find the value of this electric field anywhere inside. If I choose that point, then I need to draw a Gaussian surface on that point. So that's a Gaussian surface on that point. And we have to apply Gauss's law. Gauss's law means the closed integral of E dot dA is the Q enclosed over epsilon 0. So how do I find the charge enclosed in that Gaussian surface? To do that, as we know, we apply the formula of Q enclosed, which is the integral of rho dV. Rho is b over r squared. dV is 4 pi r squared dr. From where to where? From simply the center 0 till some radius r. Till some radius r. Okay, so from 0 till some radius r. Here, b over r squared, b is a constant. We should have mentioned that. b is a constant in SI units. In SI units. So you don't have to worry about the units at the end. Okay, b is a constant. So back to the problem. So Q enclosed will be 4 pi b. R squared and r squared will cancel. So integral of dr, it is r. From 0 to r, so it will be 4 pi br. So that's Q enclosed. Now we substitute that value in Gauss's law. We will get closed integral of E dot dA, which is E multiplied by 4 pi r squared. Integral of dA is 4 pi r squared, the area of the Gaussian surface. It's equal to Q enclosed 4 pi b r over epsilon 0. Then E becomes 4 pi and 4 pi cancels. B over r squared and r squared and r were left with 1 r, with epsilon 0 r. So this is the electric field inside that non-conducting sphere. Outside the non-conducting sphere, again, the sphere behaves as a pointed charge, so that's E inside. E outside, since the sphere behaves as a pointed charge, it's going to be qk over r squared, or if you want, it will be the q total over 4 pi epsilon 0 r squared. So let's find again q total. To find the q total, we simply use the same equation here for Q enclosed. Use the same equation for Q enclosed. Let me select this one. Okay. And paste it here. Okay, however, the limits are going to change. Instead of r, because we are finding the total Q, we are finding the total Q in the sphere. So the limit will be till capital R here. Till capital R, here I have 4 pi r squared. So it was going to be 4 pi b multiplied by capital R. 4 pi b multiplied by capital R. That's the total charge Q in the sphere. Q. This means the E out is gonna be this Q that we have found, which is 4 pi b capital R over 4 pi E0 R squared. Again, we cancel the similar terms, then finally E out becomes 4 pi cancels, so it's b capital R over epsilon 0 R squared. We plot them. So let's plot the electric field as a function of distance. So this is E as a function of R, and that's R, the radius of that sphere. So inside the non-conducting sphere, for R smaller than R, En, I got B over epsilon 0 R, which means it's a decaying curve or a curve going down. It starts from infinity until it reaches this value like that. It's decreasing, and then, so that's the electric field inside. And the electric field outside, it's B over R squared, or BR over epsilon 0 R squared. Also, I have over R squared, so it's also decreasing, but steeper because it's divided by R squared. So from that point, it's gonna be steeper now. Let's draw a steeper curve, something like that. Or it didn't appear to be steeper. Let me fix this one. Okay. Let's make that one something like that, and this one is steeper. Okay. So this is the En, which was equal to B over epsilon 0 R. This is E equal B over epsilon 0 R. You can see how E and R are inversely proportional. And the second one, E is equal BR, B capital R over epsilon 0 R squared. So you can see how E is inversely proportional to R squared. That's why the curve is going to be steeper. Okay, and that's the value at R equal R here, at R equal R. So now regarding the voltage, that's the non-conducting sphere. It's positively charged, and because it's positively charged, so the electric field lines should be directed away. And more than that, the electric field is decreasing, but since the electric field lines are directed away, this means here I have the high voltage, and as you go away we have the low voltage. So this means we should start from some high voltage here, okay, and the voltage will drop, and for sure it's positive, so the voltage is gonna drop like that. No need to know the function, but we know that it's gonna be a curve going down until it reaches a value here at the surface, and the value of the voltage here at the surface will be as if the sphere is behaving like a pointed charge, which is K multiplied by Q over R. And again, beyond that, also the voltage is going to decrease as well, because the electric field is decreasing as we move away. Exactly, yeah, and the electric field is directed away, so again from high to low outside. So that's the electric field also outside. This means I also have here high voltage and here low. So same thing, the voltage here is gonna decrease as well. So this is the graph of the voltage versus R. Thank you for watching.